Assalamualaikum warahmatullahi wabarakatuh. Good morning. Welcome to the first STEAM virtual conference in the second day and the second Keynote session series. First, let me introduce myself. My name is Elin Nishibani from Physics Department, Universitas Syah Kuala. I will be a moderator in this present keynote session. Today, we are pleased to welcome Professor Kiichiro Kagawa, a very special guest from Japan. In this session, we have 45 minutes presentation and about 5-minute question. So if you have any question, please write it down in the chat box and mention your name, affiliation, and country. The question, please be brief and clear. Okay, Professor Kagawa will present related to physics education. The title of the presentation is Frictionless Demonstration Using Fine Plastic Beads for Teaching Mechanic and Wave. It's a quite interesting theme in the physics education, mechanic and wave. And before that, I would like to brief introduction about Professor Kagawa. Professor Kagawa is a honorary professor from University of Fukui, Japan, and he got his PhD degree in physics from Kannan University. The major field research is laser-induced plasma and its application to various fields, and also he has been interested in physics education. Professor Kagawa founded non-profit organization named Fukui Science Education Academy and developed several new physics experiments since 1986. And Professor Kagawa has been engaged in the cooperative research with university and research center in Indonesia, especially Syah Kuala University. In our department, Professor Kagawa have a strong relationship with Professor Syahrunur, Dr. Nasrullah Idris, Dr. Kurnia Lahna, and also from chemistry department, Dr. Mulyadi Ramli. And up to date, he has published more than 150 papers on various topics in the field of laser-induced plasma, laser technology, and physics education. And now, we are welcoming Professor Kagawa. Professor, please.
Okay, my title is like this. First, I want to say about my attitude toward physics education. Several points. One point is try to use ordinary materials. Don't use commercial kit, which degrade children's ability. Another point, try to encourage to have logical thinking through experiment. Okay, chapter 1 is the frictionless demonstration using fine plastic spherical beads. Our introduction, mechanics is most important to understand science technology. However, in high school, mechanics is taught through training to solve calculation problem. The most unpopular subject in high school. The reason is that due to the friction, we cannot demonstrate the law itself. And another one, for falling object, phenomena finish in a short time. Students cannot see carefully with enough understanding. This is a commercial equipment for frictionless motion. Most schools use this wheel car. But not students cannot understand that this is a general rule. because this is special. Another way is the air slide truck. This is very nice, but only one dimension and very, very expensive. Our method is we use small, fine spherical beads. We scattered on the plane the plastic beads, and object move on the bead. But almost no energy loss because the mass, even they rotate, but very small mass. This is a microscopic view, 40 times. The size is roughly 0.3 milli and completely spherical. And we easily make the uniform linear motion. When we teach the principle of the friction equipment for children, we use a ping pong ball on the floor. Then we put a plate with a door, push, then smoothly move. Children very happy, but we notice, please confirm, the ping pong ball is rotating. In Japan company, Narika, sell this kind of the beads. We put the bead on a small bottle with gaze, and on the plate, we scatter the bead like shaking paper, but almost invisible. When we take out the bead after the experiment, we use a vacuum cleaner. Usually, this bead, people say rainbow beads, because in school, this bead is scattered or it used to make artificial rainbow. Beads scattered on the black paper. Then we send the white parallel or light. Then easily we can see the rainbow. Namely, the beads used as a water droplet. We published this method in physics education. This is the journal is published in England. Already 2008 we publish. But when we submit a paper, the reviewer first reject our paper. The reason is already this idea appeared in the book of Nafeel Del Revel, but they use iron ball, 1 milli, 2 milli diameter. So rather weight. The weak point is they must use heavy object like 1 kilo, cannot move. Only horizontal surface. If we incline, soon they fall down. Therefore, very limited application. Finally, we succeed publish our paper. The advantage of the bead method, our method, is easily obtainable object can be used, but should be light, should be flat, and very cheap, because one bottle is 50 US, one time only small amount, so very cheap. And important thing is that even slope, the bead can be attached by electrostatic force. Namely, we can make the frictionless slope. And student can systematic understanding is made, because all experiments are done using the same object on the frictionless plate. Also, students can touch the equipment by themselves as they like. Only small weak point is that in high humidity, namely on the table surface, there is a little water. Then friction increase. This is the object used for frictionless demonstration. This is a petri dish. This one is a lid of skin cream. Many things we can use, but should be flat and less 100 gram. If weight one, the friction increase. These are the frictionless plate. We construct this one. This is a little big, 183 centimeter long, 91 width, thickness is 6 centimeter. Weight is not so weight, 7.5. This one we construct using the styrofoam. Usually people use for building as thermal insulator, but rather flat and light. And this one, the smaller one, we usually use for a group experiment, 90, 60, 2,000. From now, I say friction plate, we call beads plate for convenience, beads plate. This big one, children can enjoy the using this bead plate, enjoy. This is the case for a PK game. There is a aim, then they try to shoot, aiming the goal. Now I want to show you a small movie. This is a small workshop for children. On the paper, there is a friction, therefore slow down and finally stop.最後。OK. Next. On the bead plate, even small driving force become vivid. This move. And we put the bar magnet on the lid and put on the bead plate, then soon rotate and this nose pole direct to the nose side. So this one high sensitive detection magnetic field. This is the compass. First, we demonstrate our first law of motion, namely uniform linear motion. Well, here, in this case, we use the aluminum disc. Diameter is 5 cm, and the only 20 gram. And this photo is taken from the top and the strobo or flashlight. Then like this, really uniform linear motion. And sometimes we use a pulse light source to record the track. In this case, 5 Hz and move, we can record using camera. This is a demonstration for circular motion. This one is a big cylindrical pipe, 30 centimeter diameter. And this is a glass petri dish. Then we start to move, then like this. We can easily see the circular motion. And this one is the cutted pipe. From here, we send the petri dish, then rotate and come out like this. Then students easily understand velocity vector of the circular motion is the tangent line. Easily understand. Now movie, short movie. Okay. And we can show the relationship between the circular motion and the simple harmonic oscillation. This is a bit plate, this is the cylindrical pipe, and we put the bright light source here, and this rotate, then we put the screen, we can see the shadow of the object. So using the projected shadow, we can show circular motion is a simple harmonic oscillation. This this move like the oscillate, like the simple harmonic oscillation. So easily understand the relation. Another circular motion we made using a string. This lid of the plastic lid, we put the pin fix, then the end of the string we hook here. Then the lid rotate uniform circular motion. And this is a strobe light for health. If there is quite no force, the circular motion keep going on like a planet motion. Also, we can demonstrate the rotation of rigid body. This is a petri dish, smaller, middle one, the center of gravity here. Then rotate around the center of gravity, they rotate. Usually this kind of image difficult for students. Also, we can demonstrate law of conservation of angular momentum. In this case, we end of string we fix so as to be coiled around the pole. Then the string becomes short and velocity increase, like a skater spin. These are demonstration of law of inertia. We suspend the weight and move with the case on the bead plate. Then case attack on the edge. Then stop. But the weight move to forward. So easily you can see the inertia. Another one is for object at rest. This is a small bead plate. On the plate, we have a big petri dish with weight. Then one person indicates the center of the object. Another person pull suddenly, but this one don't move because no transmission of force due to no friction. This is the second law in high school textbook. If we call MA, but the student not so easy to understand. Textbook, they use wheel car. And this data was not good. Also, for student, it is difficult to understand that this is a general law because this is a special tool. Our way, first, we show the quantitative demonstration of the second law. This is a blower. This one like sailboat. We push air, then move. And push, we give force continuously with blower. The speed increase. And so easily understand. Force bring the acceleration and the speed up. Then we put the weight here, for instance, 20 gram weight. Then acceleration becomes small. Roughly, student can understand qualitatively. Next quantitative experiment is we use the pulsar on the table, and the object pulsar we pull by the constant force, namely using the weight. This is the case for 53 gram. The trace like this. That's a high acceleration. If we increase the mass, smaller acceleration. This is the data from the previous photo. We can plot time and the velocity, how change. Completely linear. And this one small weight, this is a large weight. So easily, student can understand F equal ma. Next is the third law, namely action and reaction. In high school textbook, they use spring. But our method, we use the bead plate, we put the two magnets. This one fixed, then another one come close, then by the repulsion force, this bend it. Also, this magnet also receive the force, then start to move. But actually, this is not so easy because magnet soon rotate. That is difficult to control. Therefore, we construct the circular magnet. Namely, on the petri dish, in the petri dish, we put small neodymium magnet arranged in a circular form. In this case, a plastic. We confirm the magnetic field by putting compass. This is the demonstration. Two magnets. One stay here, another one outside the same pole of magnet. Then come close, then bending. Or then this one start to move. Easily we can see that there is the action reaction. Even not touching, there is the action and reaction. This is another demonstration. We use a toy of frog. We send here, then this frog jumping. At the same time, this base pushed this way. Directly we can see the action and reaction. Children are very happy. Also, sometime in the entrance examination of university, for a student, difficult problem appear. They say, please assume there is no friction on this surface. For instance, on the surface, another slope, and they say no friction, this no friction. When this object falls down, what happened? Well, this is difficult to have image, but we can demonstrate easily using the frictionless slope and this frictionless plate. And next is a falling object. This is the case for free falling object. The acceleration is g, 9.8, very rather large. Therefore, fall very fast. But in case of the frictionless slope, the force become mg, this case mg, this case mg sine theta. Namely, acceleration become g sine theta, become smaller. For instance, if with the 1 degree slope, acceleration become 1/60th, very small. Slowly they move with the acceleration. Also, we can measure the force directly to the slope side. This is a smooth slope. Therefore, we can measure the force, really mg sine theta. First, we demonstrate smaller mass, large mass. We fall down on the slope. We release simultaneously. Then this strobo photon. In the same way, they move, regardless of the mass, but very slowly. This is important. This one is we can make the quantitative experiment because the very slow motion, we can measure the time using the stopwatch, data stopwatch with rather high accuracy. Then we change the length and the time, this parabolic curve. From this, we can students derive time and the velocity. From this slope, they can calculate G dash. G dash means the G sine theta. They already know the theta. Therefore, they can derive the G near 9.8. This is a good practice for students. Also, we can measure the dynamic friction coefficient. For instance, we use the ground glass plate. On the ground glass plate, we scatter the bead. Then, in the same way, we measure the time and the distance. By changing the distance, we measure using stopwatch. This is the result, and this is the time and the square, distance and the time square. Then from this curve, they can calculate mu. For ground glass plate with a width 0.013, for completely smooth glass 0.001. This is a monkey hunting. This is an interesting topic in high school. Commercially, they sell to demonstrate this one. But in a short time finish, but expensive, near $400, and not so instructive. Our way, we use the inclined bead plate, and we use the 2 plastic lid. One becomes stone, one becomes monkey. And this stone shoot, aiming to the monkey. At the same time, monkey start to fall, but finally they attack. Regardless of speed, always attack. Very interesting. Students are very happy. This equipment to shoot, we use only rubber band. This kind of thing also we can do. What angle gives the most far distance when we shoot with the same speed? By changing the angle, we demonstrate. So 45 cases are most far distance. Next, chapter 2. This is the horizontal spring vibration in the textbook, but the concept of this horizontal spring is difficult for students to have image. But we can easily demonstrate, but we use a little big spring connect to the petri dish. We put here the weight, then slowly vibrate. We can change the mass. So we can roughly understand this equation. Once we get to the image, for students not so difficult, but without looking at this kind of phenomena, really students have a problem. This is a non-gravity demonstration. This is an inclined bead plate. In the big petri dish, we put another petri dish with weight, and there is a plastic spring. Before falling down, a little expanded, but we release. During the falling, this spring length become natural length, because no gravity. Usually, slowly we can observe this kind of experiment. Also, next, collision phenomena, also important in high school. This is a case, same mass collide. This is the small one collide with a bigger one. This is a bigger one collide with smaller one. So in this case, we use the aluminum disc. This one stop here, and another one come and collide. Then this one stop, and this one start to move with the same speed. This case is a bigger one. The smaller one attack, this stop. Then this one start to move. Also, the smaller one come back. Easily, student can see. Also, in the textbook, momentum conservation for oblique collision in the textbook. So we do using the aluminum disc. This one collide, and this one come this way. This one come like this. From photo, we plot this before collision synthetic vector like this. Then after collision, synthetic vector like this. Roughly coincide. Also, interesting experiment. We can see this kind of problem in a study aid book of high school. One exists on a table, and another come another come with a speed v to collide diagonally. Prove that after collision, v1 dash, v2 dash make always the right angle after collision. This one can derive using the momentum conservation and law and energy conservation law. But we easily demonstrate. We put one and another one shoot. Then intentionally, we don't scatter the bead around here. So this one stop due to friction, this also. And later we measure really right angle. This is also interesting. Also, important relationship between the work and the kinetic energy. On the bead plate, we measure the speed just before. This is the paper. Once arrive the paper, there is friction and slow down, finally stop. Then we measure the speed here, and we measure the distance. This is the equation. This is the work. Friction, force, and the distance. This is work. We plot. This is the x and scale velocity. Many times we students do, then plot, or we come in the same line. So really easily they can confirm this equation. Kinetic transfer to work. Usually difficult, this kind of experiment. Also the conversion from potential energy to kinetic energy, we fall down the object with different, we change the, then we also measure the velocity using the speed meter. We plot. This is a theory, this is an experiment. Rather good agreement. And we ask the student and in the slope, but this right part we scatter the bead. This side no bead. Ball and this petri, which one fall faster? Then usually people, students say, "Oh, ball faster." But actually, this petri is faster. This rate, because energy consumed to rotate the ball. Sorry. Also important demonstration. We can demonstrate elastic collision and inelastic collision. In the petri dish, we put the small plastic ball loosely. Then this case is there is a cushion. Then collide and slowly collide, then come back. Come back. No energy loss because this plastic don't move. But another case, we use aluminum weight hard ball, then collide, then this ball move randomly. Then energy loss, then stop. So energy is used for thermal energy. This is a demonstration of centrifugal force and Coriolis force. This table, on the table, we scatter bead and rotate. Then come out, finally release, then we can see the Coriolis force. Now this is a movie. A little slow motion. This on friction plate, then rotate, one more. Finally, application of frictionless plate for wave demonstration. Usually, wave propagate very fast, thus it's very difficult to observe. We made slowly propagating wave using the frictionless table. This is a big whiteboard we use as a bead plate. We scatter the beads and we put the chain of thin plastic. Plastic read the diameter 5 and the light, and connect using a thin rubber string. Then I show the movie. This end is a fixed, namely we can see the reflection wave at fixed edge. Wave come, this is fixed, then reflected opposite side, they come back, they move. Okay, next. This is a No. Same. Sorry. Stop. This case, this edge can move. Then we want to see the reflection of wave at free edge. Then come back. That's in the same phase. Okay, next. Next is the standing wave. Just fixed from this side, descent wave, like this. It's a standing wave. This is a superposed wave. Usually people use the wave machine. We show the by movie. From this side, this here, we sent a wave, same phase. This opposite, sorry. This opposite case. Come back. Same phase, then increase. Skip. This from Shakuhara University, 10 students come, Faculty of Science, to Fukui, our university, to attend the international seminar under the support of Japan Monbusho. Then they enjoy the frictionless experiment. This is a questionnaire. This I will take from Fukui University student. Before demonstration, how they feel about understanding in inertial law, second law, third law. After demonstration, completely they understand. This is a conclusion. We have proved that this frictionless method is very effective to teach mechanics and wave. And in order to make popular this demonstration method into educational field in Japan, our NPO, Fukui Science Education Academy, is now constructing the frictionless equipment by ourselves and trying to make donation for school in Fukui Prefecture. This is acknowledgement. They support our activity. Oh, this is a frictionless plate. Now we are constructing this bigger one, and this is a small component. And thank you very much for your attention.
Okay, thank you. Professor Kagawa is very interesting. And also not so expensive equipment to doing such kind of experimental. Now I'm inviting question from the audience. Okay, I'm still waiting. So before that, I want to know, Professor, when you doing those kind of module, how much time consume for one module, for example? Because we need to arrange a schedule.
You mean the time?
Yes, to
construct?
To demonstrate maybe to the student, especially when students doing kind of work.
Not so troublesome. Not so troublesome. But flat plate, flat. Then scatter the beads. And easy, very easy, not troublesome. And I hope, please, the teacher of school construct this kind of equipment. Now I have a patent in Japan, but in the future I open and release the right. And now we recommend the many students to construct this.
Okay. So we can do in very short time.
Not
so.
so.
Okay. Okay, Sensei. There's also a question from Dr. Rini. How do you suggest teacher develop demonstration method in their teaching to students?
In Japan?
Yeah, maybe in Japan or Indonesia. Maybe how about your opinion?
Therefore, now we are making the guidebook together with the movie. Then maybe easily they can follow us. So we will try.
Okay.
Is it okay? By looking at the guidebook, probably easily you can do. But I hope in the future, in the textbook, they apply this method. But there are some barrier to overcome. Because we understand only other problem is that we must use beads. And sometimes people doubt the safety of beads. But we already know, no problem. Because already the beads is widely used as a rainbow beads. So no problem. I hope that in the future the textbook use our method.
Okay. We still have time. We invited question from the audience. And Professor, bead is very small, so how to recognize? Maybe we should use typical equipment, for example, maybe camera or because
You mean the accuracy?
Yeah, to demonstrate, usually use bead, but maybe those bead is small, but maybe you use a plate to see the motion or kind of that beads only supporting. But you always use maybe camera to detect the behavior.
Yeah, sometimes we use the camera, sometimes we use the video. And anyway, everything we can share because easily we can demonstrate. The student easily understand. And if this phenomenon very fast, after take a movie, we must play with slow motion. But our case, everything moves slowly. So directly a student can understand.
Okay.
Only quantitative experiment, we must use a camera or the video.
Okay, I have one question from Dr. Julkarnain Jalil from Physics Department, Universitas Syah Kuala. Wonderful presentation, Professor. In this experiment, also possible for high school students? Of course, this is for high school students. And what do you think about the using of used material for teaching aid, especially in rural area? Yeah, maybe he mentioned about used material.
Used material, what do you mean?
Not so new material, we should buy something, we just employ the material that we have in environment. It used material.
You afraid about the environment?
Material.
After we use the beads should be correct, and the should be as a plastic should be treated as a plastic.
Yeah, maybe like you use beads or you use plate. So maybe we can use the lid of bottle to replace it. It's like a used material. So you think you can use it?
Of course, no problem.
Yeah, maybe the accuracy or the purpose is can obtain by those kind.
No problem.
Okay. Okay.
So always very cheap.
Very cheap. Okay, it's encouraging us in Indonesia. Okay, Professor.
I hope you try.
Time is proceed to next the keynote session. So thank you again, Professor Kagawa, for answer and our question, and also for great presentation today. It was a pleasure to have you with us. So the next session is Dr. Indrawati will be moderated by Dr. Mailija. So I close the session. I want to say Alhamdulillahirabbil alamin and wassalamualaikum warahmatullahi wabarakatuh.